All right, welcome to your 14th unit. This is atomic radius. Yay. So, in molecules, the attractive interaction between any two adjacent atoms is what we recognize as a chemical bond. I sincerely hope you remember that about chemical bonds. Our next unit will talk about bonding more, but as long as you remember that they actually deal with attracting things together, we're good. So, two bonded atoms are closer together than they would be in a non-bonding collision where the atoms ricochet apart. Basically, two atoms that are bonded are closer than those two atoms if they aren't bonded. So let me give you a picture. We got two atoms, and this is the electron cloud of the left one. This is the electron cloud of the right one. And I've tried to draw the dots where they're pretty close to each other. Okay, those are non-bonded because you've basically got that one and that one. Those are about the areas you'll find them in. Over here, we have the electron cloud, and these are bonded, which means some of the electrons are going to overlap. It's going to be kind of shared between them, basically. So then the actual orbitals are closer like this. And what we're saying is that this distance is less than this distance. Now, of course, I drew it on purpose to happen so, but in actual atoms, that still stays true. So, the bonding atomic radius for any atom, that's kind of a vocab term that we'll be using for a bit, is equal to half of the bond distance between the center of two nuclei of that atom when they're bonding together. Basically, it's kind of hard to figure out the radius of this atom because the electrons are moving. It's just kind of annoying. It's a little bit easier to find it if it happened to be bonded together, especially with the same self. It doesn't quite have to be, but for this case, I'm going to. What we're saying is that this is the distance between the two nuclei, but that's basically the distance of this plus this. So both their nuclei. And if they're basically the same, then our actual this radius is basically half, I don't know why I put minus, of this. So we find the radius between two of them when they're bonded, cut it in half, and we assume that's basically the radius of one of them if it wasn't bonded. So there you go. So this is typically smaller than the non-bonding radius, because again, the electrons are moving in that one. Well, they're moving in both, but typically it's a little smaller. But whenever we talk about the atomic radius of an atom, we're referring to that bonding atomic radius. It's just a lot easier to reliably do. You may be able to find the radius by itself. It's just much easier to do it this way. So by convention, atomic radius is going to refer to the bonding atomic radius. So within each group, our bonding atomic radius tends to increase from top to bottom. So as we're going down the periodic table, it gets bigger. So it's kind of like basically that, if those are representing the radius. This trend results primarily from the increases in the principal quantum number of the outer energy levels, as in they're found in higher and higher energy levels. So our clouds are, this to this to this. Like, they're just found higher out. They're in higher energy levels. That just means they're bigger. They're farther away. As we go down a column, the outer electrons have a greater probability, therefore, of being farther from the nucleus, thus causing our atomic radius to increase. That's just what we said. They're higher energy levels. They're more likely to be farther away. You have a bigger atomic radius. Within each period, bonding atomic radius tends to decrease from left to right. So that means that we've got, going this way, you're going from big to small. Now, chlorine to argon actually will increase. Arsenic to selenium will increase. Don't worry too much about that. You mainly need to care that it gets big as it goes down, and small as it goes to the right. The major factor influencing this is the increase in the effective nuclear charge across a period. So let me explain that. Well, let me let you write this down. Okay, now I'm going to explain it. The increasing effective nuclear charge steadily draws the valence electrons closer to the nucleus, causing the bonding atomic radius to decrease. Basically, overall, when you're placing electrons on the same period, you're not really increasing your energy level much. Like, anytime you're placing an electron, it's not the first one in that energy level. So let's think of, on energy level 4, or row 4. We got 4s1, 4s2, 3d1, blah, 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 4p. Okay, anytime, yes, the 4s1 technically is the first one on the 4th energy level, but then we keep adding to the 4th energy level or the 3rd energy level. Even if we go to the F block, we're still adding on energy levels where there already were electrons. Okay. However, since we're not adding energy levels, but we are adding protons and electrons, so think of this. Let me clear this real quick. Protons are attracted, or electrons are attracted to protons. Okay. And the more pairs of protons and electrons I have, the stronger this force is going to be. So, if I've got 2 protons and 2 electrons, that's kind of almost twice the force. Now, yes, the electrons are repulsing each other a bit, but you basically, it's kind of like you're attaching more and more rubber bands, and they're all sort of pulling in tighter and tighter. Drastically, not a whole lot, but when you add to the same energy level, you're increasing the protons and the electrons. They're not farther away. They're all near each other, which means they're all slowly attracted a bit more to the nucleus. Yes, electron shielding goes on, but it's not completely going to nullify the whole charge. It's just going to diminish it a bit, which means we're slowly increasing kind of our overall effective net charge, if you will. And thus electrons are slowly brought a little bit closer to the nucleus, and so our atomic radius will decrease. So, common thing that you're going to have to do is sort atoms by increasing size. Just go off the trends. If they give you one with that exception, try to remember that, but they normally aren't going to care too much. They're going to care if you know why things are increasing, why things are decreasing, or just sort them by the general trend. Well, on our periodic table, boron's over here, carbon's next to it, aluminum's under it, and silicon's here. Our trend basically says that it gets big as you go down and small as you go across, which basically means that our biggest is here and our smallest is over here. So that means that if we're going to increasing, our smallest is going to be carbon. Now, our middle one is going to be boron or silicon. I have this example to mainly show you that they won't normally give you this example. They're not going to have you figure out or remember which one's going to be closer, boron or silicon or smaller. Yes, you could probably figure it out if you wanted to, but we don't care. We're trying to see the overall trend. So in this case, both would be correct. So yes, there's an actual right answer. We just don't care. Then that'll be aluminum. So you could have put CBALSI or CBSIAL, or switch them, doesn't matter. Normally, they will give you, something like, they'll give you C, B, and AL, if you will. They're not going to be hard on you. They're not going to make it hard. They're going to basically be in some kind of a line. You just got to deal with it from there. So, there you go. That's Atomic Trend. Have fun. Thanks for watching.